Hey everybody, Dr. A here, and in this video we're going to be exploring another example of a stress-strain diagram, and in particular we're going to be generating a stress-strain diagram from tension test data that is provided to us. So let's go ahead and get started. I'm going to share my screen, and I'm going to share an Excel spreadsheet that has some information in it. So let's look at the given information. We're being told to use the data below from a tension test to plot the stress strain diagram and compute the modulus of elasticity. The specimen had an initial diameter of 0.5 inches and an initial length, or sometimes called gauge length, of 2 inches. So what do we do here? Well, first we notice that we're given a column of force in kips and elongation in inches. So from this, we first need to calculate stress and strain. Notice that we can't just plot this information because this is not stress and strain. This is force and elongation. So under solution, the first thing I'm going to do is gather the information I need to calculate stress and strain. So I have an initial diameter, which I'm going to put here, units of inches, and I'm going to say that equals 0.5. Okay. And I also have an initial length, a gauge length in inches, and that was 2 inches given to us. And then we need to calculate that cross-section area in square inches. So I'm going to do some formatting here and superscript this just to make it look professional. And how do we calculate the area? Well, we're going to say equal sign pi multiplied by the diameter squared over 4, pi d squared over 4. And there is our cross-section area, okay? Next, what I'm going to do is create a new table, and I'm going to label the first column stress, which has units of KSI, and the second column strain, which has units of inches per inch, okay? Now, how do I do this? Well, under stress, I'm going to say equals. I'm going to take that force value, and I'm going to divide it by that cross-section area. Now, if you notice, these are initial dimensions we're using, right? Initial cross-section area and initial length. So what are we going to generate here? We're going to be generating a a conventional stress strain diagram. We are not generating a true stress strain diagram. So a conventional stress strain diagram uses those initial values, initial area and initial length, okay? What do I need to do in Excel here? Well, a nice little Excel review. We want to use a dollar sign to lock in that cell for that area value, B dollar sign 23. That'll give us a vertical lock, or sometimes called a vertical anchor, okay? And then similarly under strain, we're going to say equals. We're going to start with elongation divided by that initial length of 2 inches. And again, we need a vertical lock or a dollar sign in between the cell letter and the cell number. We hit enter, okay? And then what we're going to do is drag both of these down. And notice we finally got to these values of 0. That's because we drug past the initial data. So we don't need that. We'll just delete those last two cells, okay? Now we're going to format this to make it look a little bit more professional. We're going to display maybe 4 sig figs for stress, 3 or 4 sig figs for stress, and then same thing, maybe 3 or I think it only goes up to 3 sig figs for strain, all right? Just to make it look a little more organized. And we can give this table some borders, also a thick outside border. We can maybe make stress and strain look a little bold, just to make this look professional, okay? So how do I add this plot? Well, I'm gonna go insert, and under charts, I'm gonna use the scatter plot connected with straight line segments. I'm gonna right click, I'm gonna hit select data. I'm gonna hit add, and under series X values, those are the strain values. I'm gonna highlight those. And then under series Y values, those are the stress values. So remember, strain goes on the horizontal axis and stress goes on the vertical axis. And I'm going to hit OK a couple of times. And I can give this chart title a title here. Just call it stress, strain, diagram, okay? We also need to label our axes, axis titles. Again, the vertical axis is always going to be stress, and we put the units there, KSI. And the horizontal axis for this application is always going to be strain, and we can put here inches per inch. All right. And then, we can format this a little bit nicer if you like a different font, for example. Like I like Times New Roman a lot. And we can stretch this out just to make it look a little nicer. Now, let me tell you what to be careful about. If you get too excited and you just highlight all of this data and you say insert plot and you do it the fast way, you might get a plot that looks something like this. This is wrong, okay? How did this go wrong? Well, if you get too excited and you move too quickly, what you might forget is that the first column of data that Excel recognizes is the horizontal or independent variable data across the x-axis. So what has happened here is the plot or Excel picked up stress and put it on the horizontal axis, and it put strain on the vertical axis. That's why this doesn't look like the correct shape, or it looks like the correct shape but rotated and flipped actually, which is wrong. Okay, so remember, you have to be very careful. Strain goes on the horizontal axis and stress goes on the vertical axis. So remember that from your knowledge of Excel. So this is part of the answer, right? The problem asks us to generate the stress strain diagram and to determine the modulus of elasticity. So how are we going to determine the modulus of elasticity? Where is it on this diagram? Well, it's going to be the slope of this linear portion. Now, there are a few good ways and a few bad ways of trying to get that, okay? Since we're working with real numbers, with data in Excel, this is what I would do. I would copy and paste this graph down here, okay? So you have a duplicate, okay? Then I would grab this data, and you see it highlights over here, and I would back off the data until I have just the linear portion plotted. So I still need to back this off maybe 2 more data points just to capture the linear portion, which looks like the first 5 data points. Okay, so I'm going to back this off 2 more data points. Now what I have here is a plot of just the first 5 points, which are pretty much the linear portion of that diagram, okay? Now, you might be looking at this and say, wait a second, Dr. A, this is a completely different shape. I've got this very steep linear portion in this upper graph, and I have this shallower, different shaped portion in the second graph. They're not the same. They are, in fact, the same. The reason they look different is because Excel has scaled off your horizontal and vertical axes such that it spreads out all the data in a way that looks appealing to the eye, okay, and which makes sense when you're visually looking at these plots. So Excel spread out all of the data, including the nonlinear data, to capture the full shape in the upper graph. But in the lower graph, it's only spreading out the first 5 points. So it turns out the slope of this, the shape of this, these 5 data points, exactly the same as the first 5 data points in the first graph, in the upper graph. So where do I get the slope of this? Well, the best way of doing this, the most scientific way of doing it, is right click on the data, hit add trend line, make sure linear is selected. Linear is the default, and then go down and hit display equation on chart. Okay, now when it displays this equation on the chart, what is this? Well, this is the linear equation of the best fit line through these 5 points. So if you look closely, you see this kind of dashed line that's passing nearly through these 5 points. That is a linear regression curve or line. It is a line that represents a best fit linear relationship through those 5 points. So it's not going to be perfectly through the 5 points, but it's really close, okay? And because it's not perfectly through those lines, that's why we're generating this little error here, 0.2609 that is an error that's showing up as like a y-intercept or a stress or sigma intercept, okay? So this stress intercept is not really there. I mean, in fact, if we look at our real data over here, we see that when stress is zero, strain is zero, okay? And so that's not really there. This is just kind of an error term that pops out due to the fact that you are passing a best fit linear relationship through 5 points that are very linear, linear-esque, but maybe are not perfectly linear because, again, this comes from lab data and nothing in the lab is perfect, okay? But it's pretty close to linear, all right? So where is the modulus of elasticity, or also called Young's modulus here? Well, it's the slope of this line. This is really just Hooke's law, right? E equals E epsilon, okay? I'm sorry, sigma equals E epsilon, okay? So Hooke's law, sigma equals E epsilon. So what is E, the modulus of elasticity in KSI? It is that value of 32,284, okay? And that is our answer for modulus of elasticity. And notice I did not do any kind of graphical interpretation. I didn't draw any shapes on this data. This is real data processed in Excel, okay? So it's a slightly different and more scientific and mathematical approach than what we may have seen in our other videos where we were given the sketch or the trace of a curve already given to us in Microsoft Word, okay? So that concludes this example. Hopefully you found this helpful and useful to you. If you did, please hit like and subscribe and be on the lookout for other similar content to this. Thanks for watching.